Welcome back. Unit 3, Lesson 8, Getting to the Root of the Problem. This time we're going to skip the jump start. Going to the learning focus, we're going to break down a polynomial function to find the roots. Then we're going to write a polynomial function in factored form. Our key question is, how can we find all the factors and roots of a polynomial? So it begins this way. Previously, we learned to predict the number of roots of a polynomial using the fundamental theorem of algebra and the relationship between roots and factors. In this lesson, we'll be working on how to find all the roots of a polynomial given in standard form. So let's start by reviewing numbers and factors. If you know that 7 is a factor of 147, what would you do to find the prime factorization of 147? What I would do is I would divide 147 by 7. I'd do 147 divided by 7. So I could know what other numbers are in 147. And that is 21. Then I would break down 21. Hopefully I know what the factors are of 21. 21 is 7 times 3. So that means 147 in total is 7, 7, 3, all multiplied together. Number 2, how is your answer like a polynomial written in the form p of x equals x minus 7 squared times x, x minus 3? Well, they are alike because numbers can be written as factors and polynomials can be written as factors. You can have repeated factors, like you had the 2 7s here, and you can have repeated roots or repeated factors like x minus 7. So what would I write for an answer? How about they can both be written as products of factors? The process for finding factors of polynomials is exactly like the process for finding factors of numbers. We start by dividing a factor we know, and we keep dividing until we have all the factors. When we break down the polynomial into a quadratic, sometimes we can factor it by inspection. That means just by looking at it. And sometimes we can use other quadratic tools, such as, you guessed it, the quadratic formula, which is why my classes have been reviewing how to do the quadratic formula. Okay, so let's try it. For each of the following functions, you've been given one factor. Use that factor to find the remaining factors, determine the roots of the function, and write the function in factored form. So we're going to break it down completely. Factor x minus 3. So x plus 3. So I'm going to use minus 3 along with synthetic division on the coefficients 1, 3, negative 4, and negative 12. That comes from here. None of them was missing. Okay, so how do we do this again? Well, we drop down the first number. We multiply, put the answer in the next column, and add. Multiply, answer in the next column, add. Multiply, put the answer in the next column, add. We better get a no remainder there. Otherwise, they would have lied that x plus 3 was a factor. So now, what's left here? Well, that's x squared minus 4. And since we're finding the roots, that means We need to solve to find the rest of the roots where that equals 0. Do you remember how you could do that? Quadratic formula. I wouldn't complete the square on this one. You can also use square roots. For example, you can just add 4 to both sides. X squared is 4, and then take the square root. So plus or minus 2. That means the roots are -3 and plus or minus 2. So in our final factored form, that would be x plus 3, x plus 2, and x minus 2. Our final factored form. Let's try another one. Number 4. The factor is x plus 1, so we're going to use minus 1. Synthetically divide 1, 6, 11, and 6. Draw a line. Drop the first 1. Multiply. Add. Multiply. Add. Multiply. Add. There's my 0 remainder. And what is my quotient? X squared plus 5x plus 6. Well, we're going to solve that equal to 0 to find the roots. That seems like a great candidate for factoring. So how about x plus 2, x plus 3 equals 0? So x equals -2, or x is -3. Yeah, solve by factoring. So the roots were -1, -2, -3, making the factored form the opposite of those, x plus 1, x plus 2, x plus 3. Okay, let's try another one. Factor x minus 5, we're going to use 5. Synthetically divide into 1, -5, -3, and 15. We better get a 0 remainder. Okay, drop the 1, 5 times 1. Remainder 0 there, 5 times 0, 0. Add those together. -15, perfect. Got a remainder of 0. What's left is x squared minus 3. Okay, well, this is not going to be factorable with whole numbers. We could use square roots here again. We could say x squared equals 3. Take the square root of both sides, and you'll get plus or minus root 3. That's as good as we can do with exact numbers. So the roots, 5 and plus or minus root 3. Factored form would look like x minus 5, x minus root 3, x plus root 3. Something like that. Okay, here's another one. 3 into 1, 3, -12, -18. Again, x minus 3, so I'm using plus 3. We're going to drop the 1. 3 times 1, 3. 3 plus 3, 6. 3 times 6, 18. Add those together, 6. 3 times 6, 18 again. Remainder of 0. And what is left is x squared plus 6x plus 6. If we're going to solve this, I don't think it's going to factor. We could use completing the square. I think I prefer to use quadratic formula. So quadratic formula, let's do what we call the discriminant first. B squared minus 4ac is 6 squared minus 4, 1, and 6. That's 36 minus 24, 12. Okay, so that tells me that it wasn't factorable because this is not a perfect square. It is going to be real, though. So we got to keep going. We're not done yet. We got to do x equals -b plus or minus the square root of that 12 all over 2a is 1. Now, it's a good form to take that root 12 and express it simplified. Remember, the biggest perfect square that goes into 12 is 4, and the square root of 4 is 2. So 2 radical 3, because 4 times 3 is 12, all over 2. And now if we reduce all 3 of these at once, 2 goes into 6 3 times, 2 goes into 2 once, 2 goes into 2 once. Okay, it looks like those are our roots. And so we got 3 and negative 3 plus or minus root 3. For factored form, we've got x minus 3 and then x minus negative 3 plus, it's hard not to do that, plus root 3 and x minus negative 3 minus root 3. Now, you probably wouldn't see that in the back of a textbook or an answer key. They probably would distribute the negative here and here. So a better answer might be, okay, x minus 3 and then x plus 3 minus root 3 and x plus 3 plus root 3. And that's what I would expect an answer key to show. All right, let's keep going here. We got a few more. Okay, this one is going to require some placeholders. So we're going to use 2 for our divisor, and then 1x to the 4th, 0x cubed, 0x squared, 0x, and negative 16. Then we're going to drop the numbers down. Here we go. 1 drops down, 2 times 1, 2, gives us 2. 2 times 2, 4, gives us 4. 2 times 4, 8, gives us 8. 2 times 8, 16, gives us 0. So now we have x cubed plus 2x squared plus 4x plus 8 equals 0. Now, what is another number that would divide into there evenly? It's not immediately clear what that number might be. However, do you notice we can do factor by grouping here? Take these 2 at a time. So x squared is the common factor, giving us x plus 2. And 4 is the common factor, giving us x plus 2. 0. Now x plus 2 is a common factor, and that gives us x squared plus 4, and equals 0. Now, x plus 2 equals 0. That's an easy root to get. That gives you negative 2. But then you have this x squared plus 4. Well, if we try to solve this with roots, x squared plus 4, if you move the 4 over, is going to give you negative 4. And when you take the square root, you've got imaginary numbers. This is plus or minus 2i. Hello. That's the first time we've seen imaginary numbers this year, I think. Okay, so what are our roots? We have plus or minus 2 and plus or minus 2i. So the factored form would be that the function is x plus 2, x minus 2, x plus 2i, and x minus 2i. Now it gives us, okay, I'm going to give you an imaginary number. Here you go. x minus 2i. Well, running out of time, we're going to have to patch this into part 2. See you next time. So with number 8, we have an imaginary factor, well, imaginary root right here. So 2i is going to be a root. Can we use synthetic division with imaginary numbers? I had to look that up, and the answer is yes, you can. We'll have to remember one little fact, though. So here's the setup. 1, -1, 4, -4. The fact we need to remember is that if we ever get I squared, that's equal to -1. This is something that you got in the integrated 2. All right, so let's try it. Bring down the 1, you get 2i. Then you're just going to have to write 2i minus 1. Now, that's a complex number. It is thought of as a single number, 2i minus 1. Now, we're going to multiply that times 2i, but we'll have to distribute it. So off to the side, 2i times 2i minus 1. You're going to bring it in. Will be 4i squared minus 2i. But now here's where we bring in that fact. I squared gets substituted with -1. So right here is -1. So that will be -4 minus 2i. That's what we put on the next column. That will work out nice because the 4 and the -4 will cancel. We'll get -2i. Then we're going to multiply 2i times -2i. So let's see, 2i times -2i is 2 times -2 is -4i squared. But remember, I squared is -1, so this is just +4. And it does work out with a remainder of 0. Isn't that cool? Now, what about the stuff that's left? Well, that is yucky looking. That would be x squared plus 2i minus 1x minus 2i. Now, I don't know about you, but I really don't know how to do that. Like, what should I even do with that? So we have to bring in something else. Let's go back to the quadratic formula for a second, because really that's where these complex numbers started. So you have x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now, let's suppose that b squared minus 4ac is a negative number. Well, you're going to have plus or minus with an imaginary number over here. So that tells me that if 2i is a root, automatically -2i is going to be a root because of that plus or minus in the quadratic formula. So let's do this. I'm going to have to erase some of this stuff here. Make some room. Let's take -2i. Okay, because if we have 2i as a root, then -2i should be a root. And let's go with what we have here. And that's 1, 2i minus 1, and negative 2i. Let's see if we get a remainder of 0. Okay, so we drop down the 1. Then we get negative 2i. Oh, look at that. It canceled. 2i minus 2i is no I. It's just negative 1. And then negative 1 times negative 2i is 2i. And there's your 0. Then what's this part? Well, that's just x minus 1. And if we set it equal to 0, that means x equals 1 is a root. So 1, 2i, and negative 2i are the roots. And it's degree 3, so there's all the roots. 2i, negative 2i, and 1. So the factored form of the function would be x plus 2i, x minus 2i, and x minus 1. It's pretty cool, right? So, is it possible, number 9, is it possible for a polynomial with real coefficients to have only one non-real complex root? So, complex root, that means it's got I in it. Is it possible to have only one answer with I? And the answer is no, since in the quadratic formula, there's a plus or minus before any root of a negative. And that means plus or minus something times I. So, number 10. Based on the fundamental theorem of algebra and the polynomials that you have seen, fill in the table in the takeaways to show all the number of roots and the possible combinations of real and non-real complex roots for linear, quadratic, cubic, and quartic polynomials. Okay, so before we do this table, I just want to point something out to you, is that when you have a plus or minus of something, so something of the form a plus or minus b, this is called a conjugate. And it's related to a word that means to be married. A and B are kind of married together. Actually, it would be a plus b and a minus b are married together. If you have an imaginary number, a plus or minus bi is a complex conjugate. So what we just discovered in number 9 was that if you have a complex root, the conjugate is automatically a root. So that means they come in pairs. They come in 2s or 4s or 6s. They never come in odd numbers. You'll never have an odd number of i's unless the polynomial doesn't have real numbers in its coefficients. And that's why it said in number 9, let's see, in number 9, is it possible for a polynomial with real coefficients? No. If they're real, then the complex roots will always come in pairs. So let's go to number 10 here. Okay, so a linear will always have one root. A quadratic will have 2 roots, maximum. A cubic will have 3, and a quartic will have 4. So the degree matches the maximum number of roots. So that's why back in integrated 1, you can only have real solutions. There's no room for imaginaries. If there's only one and they have to come in pairs, it's not going to work. Okay, if it's quadratic, you can have 2 real roots, or you can have 1 real with a multiplicity, or you can have 2 complex, right? It contains I. If it's cubic, okay, think of all the possible combinations. You could have 3 reals, or you could have 1 real and 2 complex. They didn't leave me enough room here, did they? You could have 1 real of multiplicity 3, or you could have, let's see, there's one more possibility out there. You could have 1 real with a multiplicity of 2 and just 1 other real. See, it has to add up to 3. So quartic, all the combinations of that. So you could have just 4 real. Or you could have 1 real with a multiplicity of 4. Or you could have 1 real with a multiplicity of 3. And another real. You could have 1 real multiplicity of 2 plus another real with a multiplicity of 2. You could have 2 real, but then there would have to be 2 complex. Or you could have 4 non-real. We'll have to do a Desmos side lesson on this, because this will show up in the graphing as well. Here's that vocabulary I mentioned earlier, a conjugate pair. So A plus BI. Let me give you an example. So if 2 plus 3I is a solution, is a root, then also 2 minus 3I is a solution or a root. Guaranteed. As long as the coefficients of the polynomial you start with are all real. That's something to really think about. Okay? Deep. Definitely deep. And kind of completes the story of polynomials. So human beings had been thinking about this for a long, long time before they came through with these theoretical breakthroughs. So in this lesson, we learned, what did we learn? To find the roots of a polynomial using long division. We actually use synthetic, right? So synthetic. And factoring to break down, not just factoring, we also did quadratic formula, to break down the polynomial into factors of lower degree. Technology is useful, we didn't really use it, but is useful for checking work and finding real roots that can be used to find complex roots. We determine the number and type of roots possible for each polynomial, which will be useful in writing equations and finding roots in upcoming lessons. We still have 2 more lessons to go. So we'll see you guys next time.